economic lot size. So suppose that we're manufacturing a product and we have some things to consider in balancing out costs, and that's the heart of this problem. We need to make some assumptions first. So suppose our company manufactures, So we manufacture a constant number of units of a product per year. That keeps things simple. Now, that's not very realistic, but we have to start somewhere to keep things a little simplified. And also, we're going to say the demand is constant as well. Again, not very realistic, but we'll just roll with it. But we're also thinking in terms of years. Another assumption we're adding. So we want to manufacture these equal batches. So same number of cases of some product within each batch. And this will be at even intervals throughout the year. So it could be, for instance, once a month, something like that. Our ultimate goal is to minimize cost of doing this, but we have a couple things to consider, and it's a bit of a tricky balancing act. So we could just make one batch, which would seem good in some ways. That would minimize manufacturing costs because we're not manufacturing as often. But the downside is that this would lead to greater storage costs. So in that sense, we would have a higher cost. So, but we would have higher storage cost or warehouse. So it probably would not be very economical to make everything all at once in a year. On the flip side, if we produce a bunch of batches of our product like way too often so that we're basically never using storage, well, we would minimize storage cost, but that would maximize manufacturing cost. So I'll add that. Or we could produce many small batches. But the downside is that this would increase manufacturing costs. So our goal with an economic lot size problem is to balance this out so that we minimize cost overall. So the ideal number of units per batch. So for example, how many cases of the product do I make with each batch? That's the question we're addressing here. And we call this Q, which is the economic lot size. so the ideal number of units per batch is Q, the economic lot size, which minimizes cost. That's the goal. It's not obvious how we balance those manufacturing costs with the storage costs. We're going to need to take a look at all our variables at play here. So the first one is Q, which we just mentioned. The economic lot size. So in particular, we're talking about a number of units per batch. Whoops, per batch. And that's what we're saying with lot size. Well, we have some other variables at play. Well, Q is the main variable. K is the cost of storing 1 unit for 1 year. Remember, we have storage costs because we're not using everything all at once. So K will be the cost of like 1 case of our product for 1 whole year. That cost of staying in the warehouse. So F is the fixed setup cost. For manufacturing. That's why it could be more expensive to manufacture too often, because you have this cost showing up. G is our next variable. Well, this is the cost of manufacturing 1 unit. And our last letter here, capital M. Remember we said that there was a fixed number of units that we produce annually. It's one of the first things I said here. So M will be this total number. So this would be like the number of cases that we produce in a year. So our main variable, which is a variable in the true sense of the word, is Q. It's the main thing we're looking for, the economic lot size. How much should I produce in a batch so that I minimize my balance of costs? And the rest, they're like a fixed start of the problem. We're going to work towards solving Q, which gives a minimum cost. So we need to start setting things up. First, the cost per batch. So the cost of producing a single batch, well, let's put equals. That would be the fixed cost. Remember, there was this manufacturing cost, which was just part of setting things up. So you have that going on. And in addition to that, you have the variable cost, which actually has to do with the number of cases that you're producing. Okay, so the fixed cost is just the letter F we mentioned above. And the variable cost, well, we know G is the cost of manufacturing 1 unit. So that's certainly involved. But then you multiply that by the number of units you have in a batch, which will be Q. And now that leads us to the total manufacturing cost. That's going to be the cost per batch So that's the cost of a single batch times the number of batches you have. So the cost per batch, that's what we found up here. F plus GQ is the cost per batch, and the number of batches is M over Q. Now, why is that? M is the total number of units that we produce annually. So think like cases of honey. And that's going to be the example I'll do in a bit. So the total number of cases cases of honey that we produce in a year. But that's all done within batches, separate batches. And Q is the number of units that we have in each batch. So if you take the total number of units overall and divide by the number of units that's in each batch, that gives you the number of batches. So think of this essentially as how many times we're manufacturing in a year. And notice that we have some things happening with the Q here. We get a little canceling right there when we distribute. But we'll have an FM over Q plus GM. And in this one, the Q's cancel. So this is the manufacturing cost. That's one of the things we have to balance. But remember, we have storage costs as well. Right? So the storage cost and then we'll combine these two things to get the overall cost, and then we'll be set up. So for storage cost, that's going to be the cost per unit times the average number of units in storage. And we won't go too deep into this. The book covers it in a little more detail than what I'm going to do here. But the cost per unit, that was one of the letters we had specifically. This one, the one we haven't used yet. So the cost of storing one unit over a year, that's K. And then the average number of units that are going to be in storage is Q over 2. The number of units that are in a batch divided by 2. We won't go too deep into that, but the book lays that out, why it's that specifically. Or we could put that all together. Doesn't matter too much. There, so that's going to be our storage cost. That's a bit of an approximation, but we have to do that. And here's manufacturing. So our total cost overall will be just these things added together. And this is what we're trying to minimize. So I'm going to call this T, and it's going to be a function of Q, because Q affects it. Q is our main variable. So again, it's just the manufacturing cost plus the storage cost. So FM over Q plus GM, that's manufacturing, plus storage. So this is what we're trying to find the minimum of. Let's take a look at our domain real quick. Again, Q is our primary variable here. The rest are going to be fixed numbers in a problem. So when I ask about the domain, I'm asking what Qs am I allowed to have? Well, you can, on the low end would be 0 units in a batch, but we don't quite get there because we're making something, right? So I'm going to put an open interval there. We don't quite hit 0, but that is essentially our low end. And M would be our high end. Again, that was the number of units that we just make in a year altogether. So in that case, that would mean I'm only making one batch. I'm just doing it all at once. All M things are being done in a batch. So our goal is to minimize T of Q, this function, because we're trying to minimize cost. To do that, we're going to have to take a derivative. So T prime of Q remember, Q's are variable. It's like our X. These other things are just going to be fixed numbers, so I kind of ignore them, treat them as constants. Right? Notice that this does not involve Q at all. So the derivative there will be 0. It's just constant. And here, since Q is just to the power of 1, we're just going to get that coefficient there. So you set that equal to 0, and then solve for Q. Okay. Well, for the purpose of time, I'm going to skip some of those steps. It's not too challenging. You'll end up having to take a square root, but we don't do the plus or minus thing here because it doesn't make sense for Q to be negative. And this is the economic lot size. This is the amount of units I want to produce in a single batch, which will minimize that balance of manufacturing costs with storage costs. Let's do an example. So let's say a manufacturer has a demand for 9,300 cases of honey every year. And now it costs $6 to store one case. For 1 year. So that's the storage cost coming in. Also, $31 in setup costs to produce each batch. Okay. And then $17 to produce each case within a batch, of course. So each case of honey costs $17 to make. Now, with these manufacturing costs and storage costs at play, we want to know what's the right balance of cases of honey to produce within each batch that we make, which will minimize our overall cost. So in particular, find the number of cases per batch to minimize cost. And so when I say this, I'm talking about the economic lot size, Q. So we're just trying to find Q. So this is the Q that leads us to that minimum cost. So we have to find all those variables. Notice it's interesting that G doesn't even show up in there. That was one of the variables, but turns out it doesn't really have an effect. All right, so that first, or the first letter I listed earlier, I'll start there with K, letter K. That was that main little part of the storage cost, which was the cost of storing 1 unit for 1 year. Well, we see that right there. So K is 6. It's how much it costs us to store 1 case of honey for a year. All right, my variable F is that fixed setup cost for manufacturing whenever we're going to make a batch. That would be this right here in setup cost to produce each batch. So F is 31. I'll go ahead and find G, but it won't really affect our problem. The cost of manufacturing 1 unit, in that case, we're talking about, well, cases of honey. So G is 17. It's actually not used in the formula, turns out. Finding Q. And that last variable, besides Q, is capital M. That was the total number of, in this case, cases of honey that we produce in a year, which was one of the first things I said. So then Q, we just follow the formula. Square root of 2 Fm over K. This will get us the Q, which minimizes our cost. Again, I'm not even using G, turns out. And should get 310. And so what I'm talking about here, remember, is cases per batch. Okay, so most problems you'll encounter in the homework, it'll have this part, and then it'll ask you one more thing, which is very closely related. So I know how many cases of honey I want to make in each batch. Well, how many batches will be produced annually? Very closely related to Q, just not quite the same thing. And actually, kind of mentioned this before in that big setup I was doing. This is that M over Q number. This is how many cases of honey I'm making overall in a year, divided by the number of cases that are in each batch. That will lead you to the number of batches that we make in the year. So if it helps, I'll just write out these units. Think of this as cases canceling out, and batch can end up going into the numerator. So we're calculating batches with this figure. That's how the units work out. So M over Q, 9,300 over 310 means we're going to be making 30 batches in a year, evenly spaced out. Okay, before we move on, you will see a slight variation of this with like ordering something instead of manufacturing. So the example you'll see in the homework is like a restaurant ordering bottles of wine. And I'm not going to do an example here for the sake of time and because it really just shakes out in the same way. The formula is the same for finding Q. It's just that F doesn't quite mean the same thing because we're not doing the manufacturing in this case, but it's analogous. So when we're doing the manufacturing, F is the setup cost for producing each batch. But in the case of like a restaurant ordering supplies, then that is analogous to the cost of ordering something. So it's pretty similar, but just that slight difference. But then it's really the same formula. And another difference is that G plays no role in those ordering problems because that's a manufacturing cost. But notice that it didn't really matter for our formula anyway in the end. Okay, so I do want to move on to elasticity. So this is a different topic, but still within business applications. In particular, let's give the full title, Elasticity of Demand. So this is a way that we analyze demand relative to price. Like if I increase the price of something, that may have an effect on the demand. Like if I make something too expensive, then people aren't going to want to buy it. So this leads to some interesting calculus applications, which are important for business. So elasticity of demand. Let's say P is price. And this could be a little confusing, but I'm going to stick with how the book does it in Pearson. We have a Q. This is not the same thing as the Q we just talked about. Totally different. Here Q is demand. And I'm going to write also F of P. By that, I just mean that it's a function of P. It depends on the price. That affects people wanting your product. So I'm not going to totally derive this here. You could look at it in the book if you're really interested. But the elasticity of demand we call that the letter E. And the formula in particular is the negative of P over Q. And remember, Q is a function of P. So the derivative of Q with respect to P. We say the demand is inelastic. So this is with one particular outcome when that E number ends up being less than 1. So if we work out this E here, and it's a number less than 1 with my specific price, then the demand is inelastic in that case. And I'll explain what that means. We have the opposite. The demand is elastic if E is a number bigger than 1, so it all has to do with 1. And the other outcome is, what if it's equal to 1? Then we say that demand has unit elasticity. Think of unit means 1, basically. So that's when E is 1. Okay, so we can square that off. I've got an awkward page break here. But there's our formula and the various terms. So let's underline unit elasticity. Okay, great. Well, what do these things mean? What does it mean for demand to be inelastic or elastic? So again, we're thinking about, how does the demand for our product change when we affect the price, or when we increase the price, mainly. So let's focus on that less than 1. That's the inelastic case. So if demand is inelastic, that means that if we do a small change in price, it won't have very much of an effect on our demand. So it's not very bouncy or elastic in that case. So small change in price will have very little effect on demand. Now that sounds desirable at first, right? Because that means that we can hike prices. Excuse me. We can hike prices, and it's not really going to affect too much how much people want our product. But we'll actually see that this is not necessarily ideal in terms of the revenue that we take in. And the reason being is that, well, the reason that you're inelastic like this is probably that your price is just too low in the first place. So that's why this is not necessarily ideal, even though it sounds good. Well, we certainly don't want elastic. If E is greater than 1, then that means if we change our price just a little bit, that will have a big effect on how much people want our product. So let's say the relative change in demand is greater than the relative change in price. So that's not really ideal for us. And I'm going to show this to you in a bit, but it does turn out that the ideal situation is unit elasticity. So that means that the change is the same between the two things. Okay, so the percent change in both price and demand are the same, are relatively equal. Okay, so let's look at an example. This demand for air travel. So notice I haven't really brought revenue into the picture yet, besides just mentioning it in passing. We'll get there. But I want to start with this example. So let's say the demand for air travel between two cities. We'll do a pretty simple one for the sake of time. Remember, demand is a function of P. It depends on price. Okay, so we want to find the elasticity of demand at a particular price. So when the price is, let's say, $166.31. So we're talking about particular travel between two cities here. So E, just follow the formula. That's negative P over Q times the derivative of demand, Q, with respect to P. Why is this negative here, by the way? Well, that's because there's like an inverse relationship between price and demand. If you increase price, then demand is going to go down. So by throwing in a negative, that makes it so that E is a positive number. So that's why that's there. So Q, we have a formula for it. We want to get everything in terms of just P, one variable. So 55.1 minus 0.025P times the derivative of this function, where P is the variable. Well, this 55 will go away, and we'll just be dealing with that part. It's just that constant is the derivative. So this is the general formula for elasticity. But now we need to plug in this particular price to find out the elasticity when we're at that point. Okay, so I'm going to use this notation where I'm evaluating at P equals 166.31. So just plugging that in. And I'll just cut to the chase here. This is what I got. So that's certainly less than 1. Less than 1. That's the important thing here. How does it compare to 1? Well, we're less. So that means demand is inelastic. So if we raise our prices a little bit, that's going to have very little effect on people's willingness to go to do this air travel. So that sounds like a good thing, but again, that's actually not necessarily going to give us the most revenue, as we'll see, because our prices are probably too low in the first place. So that's, as a company, that's our real important metric, right? Is how much revenue are we getting? So how does this affect revenue? Well, R is P times Q. Okay, the price times the demand. Q here is a function of P. This is actually a great lead into the next lesson. This is a function of P. So really R is just a function of P overall. What I'm saying is that I can take the derivative of R with respect to the price P. So how is revenue changing as the price changes? What's the rate of change? I'm going to do product rule because, again, Q is a function of P. So that means I do need to do product rule. I'm being very general here. So I'm just writing derivative of Q with respect to P. So that's product rule. I did P times derivative of Q. And now derivative of P with respect to itself times Q. So that's product rule. So we're getting, our goal here is maximizing revenue. That's why I'm taking the derivative. I want to ultimately figure out where is this zero. That would give us a maximum. So that's where we're headed. This here is kind of a weird step, but we'll see why it helps. I'm going to multiply this part by Q over Q. Now that doesn't fundamentally change what's going on here. This is like times 1, but it's going to be helpful to have it there. Because if I move this Q over here beneath the P, well, then we're close to the elasticity formula. So I'm just moving this over. I can do that. So this here is E, but the negative of it. We had a negative in front in our E formula, which we see up here. Okay, so that's why I threw in the Q over Q. So this is Q times the negative of E plus Q. And notice I have a Q in each term. So I factor it out. And that's pretty good. I just want to clean it up a little bit, perhaps. So this is the same thing, just looks a little nicer. So this is the rate of change of revenue with respect to price. So as I change my price, that's going to affect revenue, and this gives us that rate of change. Our goal is to maximize revenue. So we basically want where this is 0. And I'm even going to make a little graph here, which roughly shows what's going on. We have revenue R, the money we're taking in, as a function of the price that we set. It's going to have this kind of bell curve shape roughly. This may not be super exact, but gives us a pretty good picture of what's going on. Right, so we have right here in the middle, that's our maximum. And that's what we want. We want maximum revenue. Well, it turns out that that is when E is 1. When the elasticity is 1, or we have unit elasticity. Because, notice up here, if I plug in 1 for E, I get 0 for my derivative. So this is when dr dp is 0, that's a maximum. Now, how do I know that it's a maximum rather than a minimum? Well, I'll show you in a second. I mean, obviously it looks like a maximum in the picture, but I haven't told you why this picture is true. So what's happening over here on the left, this is when our demand is inelastic, when E is less than 1. And I'm writing it over here because E and the price, P, are related. So think less P or lower price means less E. And you can kind of see that in the formula. And you can kind of see it here. If P is a smaller number, then certainly this part will be smaller. But I think it mainly comes from the concept, what's happening conceptually. Okay, if I have a lower price, then that means that an increase in price won't have a very large effect on demand, right? So we will be more inelastic. So that's why, this is technically a p-axis, but I can also just write e less than 1 over here, where we have lower p-values. And the reason that matters is a little long-winded, but the reason this matters is we'll look at what that happens to our formula here with the derivative. So if e is a number smaller than 1, that means that we will be positive. So dr dp will be positive on this side. And that's how I know I get this sort of bell curve shape. We're increasing on the left side. We hit our high point, our maximum, in the middle when e is 1. And then the derivative will be positive on the other side, or excuse me, negative. And that is when we are elastic, when e is greater than 1. If e is like 2 or something, then we'll see here this is negative. So I know this is a maximum because we're increasing on this side. So this is basically first derivative test. We're increasing, then we have a critical point here, and then we're decreasing on the other side. That's a maximum. So this is why our ideal situation is to have unit elasticity where e is 1. So finally, and for the sake of time, let's use our previous example with the air travel. So let's go back. We saw here that the demand was inelastic. It was less than 1. But that doesn't necessarily give us the most revenue. It means that our price is probably a little too low. So the sweet spot is getting e to be 1, and so we'll figure out our price based on that, our new price that we want to make. So this is one of the key takeaways. Revenue is maximized when e is 1. So we had our formula for e. I'll just kind of copy it again. This was our general formula for e, and times this negative here. Well, I want to set this equal to 1 so that I can find our price, which will give us the most revenue. And so then we solve for p. Okay, so these here can multiply together. This denominator here, I want it to go away. I don't want it to be a denominator. So I'll multiply both sides by that. And that'll be a times 1 over here. So let's start on that right side. Got this 55.1 minus 0.025 p. So it was this whole thing times 1. I'm not going to write that times 1. Right, so I essentially moved that over. And now bringing these things together, multiplying them, double negative goes away. So that's a positive 0.025p. And now I can add this guy to both sides. Remember, I'm trying to find P. So I just added this to both sides. And then it's just division. So this is the price which will maximize our revenue. So 1,102 is what I got, dollars. So that's a lot more expensive than it was a 166 number we had before. That 166 number was probably too low. That's why our demand was inelastic. Now that's why if we were to increase the price, it wouldn't affect demand hardly at all. So this is the sweet spot. It's going to maximize our revenue. All right, that was a fun little dive into business applications. And next time we will be dealing with implicit differentiation.